need bigger classrooms. The numbers are fine for us.
So I don't know, but which year you got it? 2014.
Yes.
Yeah.
Hello. 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 Fine.
There's a nice ring to it. Yeah.
What?
Kevin, your new name, Kevin. Kevin. Yes, to USC next year.
Here too.
I think we can start.
Started there. Okay.
Okay. Good afternoon, everyone. I hope the pizza was good and we're still awake. So let's talk about the sort of the our results. So this is published in Fox this year. There's joint work with Rohan Guge and Vishwanath Nagarajan. Rohan just finishing his postdoc at Georgia Tech. He'll actually soon be joining UT Austin Business School. And Vishwanath Nagarajan, who's in UMich Iowa. So yeah. So this work basically is a very interesting sort of problem that so I always knew about. Oh, sorry. Yeah. Okay. So I sort of was always familiar with the framework of multi-arm bandits, where you learn repeatedly, right? You don't know the environment, you don't know the environment initially, and you iteratively learn. And by iterative learning, you approach the sort of best policy or the best arm, and you sort of you do that smoothly. If you characterize that exactly in terms of regret, like your regret is a function of the time, as we saw. Okay. Now, around 2019, I got introduced to the sort of world of stochastic optimization, and which is basically combinatorial optimization, but with a stochastic flavor, right? So, let's say you are placing sensors in an environment, and you maybe some of the sensors can fail, right? So, sensor placement is a classical submodular optimization problem, but maybe sensor failing adds some stochastics, right? And then um, there are many such problems that have sort of this underlying stochasticity. One problem that intrigued me is called Pandoras, which is basically like a which is called optimal search. Again, a stochastic optimization problem. So, okay, given all these problems, the next natural question that came to my mind is how does, like, since these stochastic optimization problems depend on you knowing the distribution, right? The optimal solution depends on your full knowledge of the distribution. The natural next question that came to my mind is, okay, suppose you don't know the distribution and you want to learn this on the fly. Like, let's say you're repeatedly solving a problem. Let's say you're optimized your scheduling or your sort of how your airline ticketing prices work and so on. And uh, you're daily solving that problem, and you want to learn the parameters of the distribution of the environment on the fly and smoothly approach the performance of the optimal policy, right? So how do you do that, right? And in the literature, there was several sort of results for some problems. This is called like offline to online conversion, where you take an offline algorithm and you try to convert it to online. And it's very sort of messy, dependent on the problem and so on. And what you're thinking, like, maybe that's a very simple solution works. And essentially, after talking to several like these people and so on, this is basically the culmination of that thread, and we actually had a very nice result for many different problems under one framework. Okay, using a very simple algorithm. So the analysis of this is basically the main result. So let me first give you a very brief sort of introduction to stochastic optimization. Like not an introduction really, it's just describing some problems. And maybe we can have another lecture where we go into like the stochastic optimization results for specific problems. But today I'll just give you sort of a few problems to just get us started. So one very basic problem is like series testing, just to sort of okay. So now this is far away from the bandits world. I'm not talking about bandits at all. This is different. So you have in series testing you have n components. Yeah. And so PI is the probability that ith component is okay. Okay. So you have, let's say, a machine or a assembly line or whatever. There are several components in that, and each component can fail with certain probability, and PI is the probability that ith component will fail. Okay, and this is known. Okay, so in this setting, this is known. And then CI is basically cost of inspecting I. So if you want to inspect whether this component is working or not, you pay CI cost. Now, your goal is to verify whether the system is working or not, meaning that all the components are basically working. Okay. So if a component is failing, you want to quickly detect. So if a component has failed, you want to quickly detect which component has failed. If you can't detect any component has failed, then you basically have to iterate through all the components. So what should be the order in which I should inspect?
PIs are independent.
Yes, that's important. Yes. It's very important. In all this work, individual components or individual items will all be independent. Very, very important. That's a huge another sort of now box that we haven't opened. So, but here we will just sort of assume that everything is independent. Yeah. Okay, so what should be the order? Yeah. So just greedy, basically. Okay, so you have 1 minus PI divided by CI. So this is basically the probability of it failing divided by the cost, and this is basically so sort in decreasing order or sort of open or inspect.
So assume you know the probability separately.
Yes, here the probability is assumed to be known, and that's when we'll come to the next question. What if the probability is not? Okay, so the next problem is very nice.
Just to be pedantic, can we just do the argument for this? So, so 1 minus PI is the probability for it failing. And so you're saying that if I do it I just want to see the proof flavor. Is it like a switching argument or? So
Yeah. So for this it would be yeah, it's a simple switching argument. Yes.
So if you
Yeah. So if you just reverse and keep on iteratively reversing
switch,
switching, and then you possibly
expected cost.
Expected cost will be
What's the objective is?
objective. Oh yeah, sorry. My bad. Okay. Yeah. So minimize some overall yeah. Okay. And basically S is the set of items that you have inspected, and it should be like it should be the case that at least one of this S has failed, or none of, or it is the complete set. Like that's a constraint on S. Either it's the entire set of items or components, or at least one of them should have failed in that particular realization. So remember, this is a stochastic environment, right? So so it's basically a policy. Okay. And this is a very loose definition of the problem. I'll come to the sort of more proper definition of the problem. So you want to minimize over all policies which have a particular constraint that they inspect boxes in sequential order, right? And they can only terminate if either all the boxes are inspected or at least one of the component is sort of found to be defective.
So that capital S is given by like we inspected
Yeah. So okay.
When we fail for the first time,
Yeah.
that prefix will be my S. Otherwise, it will be like S.
Yes, exactly. Yeah. So yeah. So let me just even
Optimizing or all possible orderings or
all possible ordering can be adaptive also.
If it is independent, adaptive, and non-adaptive.
Yeah, for this problem, yeah, it doesn't. So you minimize over all possibilities. X is the random variable, and then S sigma X is the basically the sort of set that was inspected, given policy sigma and X. Okay. So question. Okay. Okay. So Pandora's box is completely different flavor of a problem. It actually comes from the economics literature, and so there was this is a very famous called Weizmann policy, and so this problem was sort of encountered in the setting of optimal search. Okay, so let's say you have n candidates that you can potentially hire, and CI is the cost of inspecting or sort of interviewing candidate I, and you want to select one candidate. So, in which order should you invite these candidates? Like that's the question. So maybe you should invite like the best candidate and so on, but you can only hire one candidate. Like that's a constraint. Okay. So again,
unlike stuff, the other thing, it's not unlike like secretary problem, it's not irrefutable. That is, you can go back and say
you can go back to that's an important distinction. Yeah. You have n boxes, okay, and xi drawn from di, basically the reward for box I. So this is the random variable. This is the D is the distribution, and Ci is the cost for opening I. And the goal is to again adaptively so this is the objective function for Pandoras. So you want to maximize. So that was a minimization. This is the maximization problem. You want to maximize overall policies, and this. So this is a product distribution, again, like independent random variables, and you can only take one of them. You'll assume that you'll take the max, right? So max realization out of the set that you have inspected minus the total cost that you spent. So very interesting. For this problem, again a greedy sort of algorithm work. It's called the Wheatsman. The policy is called Wheatsman policy, and maybe in the next lecture we can go into this and then see the results specific to this problem. But I just wanted to quickly introduce some examples.
What is the greedy algorithm?
So you can calculate what's called a reservation price, and you order based on the reservation price. Okay, and as soon as some xi becomes greater than the reservation price, you stop at that point.
You know the distributions? Yeah.
Yes, yes, yes. So everything here in the this is a classical setting I'm talking about, not the online setting. You know the distribution. You know for the series testing, you know pi. For this, you know the xi, the di basically.
Can you describe what exercise is?
Oh, xi is the random variable for the reward.
Oh, okay, got it.
Xi is the random variable for the reward, and di is the distribution. Just yeah.
Both the algorithms here are non-adaptive because we are stopping after like VC. In this case, we are stopping after VC the first call.
You call them adaptive, yeah, because stopping rule is adaptive. That's the important point.
It's very much like profit inequality. Albeit you are not required to stop it, though you do. It's just that
Yeah.
you don't have to stop there.
Yeah.
I mean,
For optimizing the cost, you will.
yeah.
Okay, so and the third one is like it's just another thing that I have looked at before. So I call it sensor placement. Some people will call it stochastic. Although our results for this problem are sort of limited, so that's why I stick to this problem of sensor placement. For general submodular stochastic submodular, we don't really have results. Okay, so you have n possible sensors. And you have a coverage function. So actually, so basically pi is the probability of sensor I failing. Okay, and there is a coverage function that basically 2 to the n to some real value. This is so assume this is a submodular function, and essentially your goal. So now again it's going to be adaptive policy. You place one sensor, see if it is failed, if it fails or not. Okay, based on basically whether it covered the particular area you decided to cover it, you choose another sensor. If it fails, you maybe want to cover the same area with another sensor. If it didn't fail, you maybe looked at another area and so on. So it's again an adaptive sort of policy. And your goal is to minimize okay. So basically like this is you want to minimize your expected cost. Minimize your expected cost subject to the policy being such that this is deterministically covered. Assume that one item is like very high cost and covered everything. So this thing, the f of s sigma x is greater than q. So now this is note that this is a stochastic submodular function.
Such that
F of s sigma x. Q is some lower bound. Like let's say you want to cover this area.
Coverage.
Coverage, yeah.
it's a generalization of series testing in some way that I mean in this case components can overlap or like it's power set of components and
Can you think of it as generalization?
Yes, I mean, your coverage function is just
Just yeah.
indicator of one thing failing.
Yeah. would that be submodular?
Okay, so even the point is that okay, there's a stochasticity in failing, whereas f is a deterministic function.
Yeah.
No,
F is so F is a look, so F is a n dimensional sort of function,
yeah,
and if ith guy fails,
yes.
then you replace that by ith thing by null
Okay,
or
so f of s is like a loaded.
yeah, it's a loaded thing. Yeah.
So it's okay. The same way as there, you have to ensure that at least one of the component failed. Here, you have to ensure that, like, you can think of it like it does capture that.
Yeah.
There's a signal like a. You think of it as covering the.
Yeah.
Like failure being like your area of coverage is just failure as soon as one of them. This is a generalization, but f of s is a slightly sort of technically involved thing because it's not a like s itself is a random function.
Yeah, so okay, if you want to make it simpler, you make it a deterministic function,
Yeah.
but then have like s bar of where s bar is basically number of surviving tensors in S sigma x.
You have to keep adding sensors till this function crosses this.
Closer, yeah.
And so your policy has to ensure this.
Policy has to be a constraint in the policy. Okay, yeah. So
So, like the function f, you have given oracle access to it at any point of time, or
yeah, let's say you have given order access. Yeah. Yeah. Yeah, so the idea behind this is that I think it's a bit unsatisfactory to see the problem and not see the solution. But what the solution that I want to show is the bandit solution. Okay, and so we'll assume that there exists one algorithm for this. That given the knowledge of distributions, in this case the probability of failing and so on, and again this is independent. Given the knowledge of the distributions, you have an algorithm that either exactly solves the problem. So in both cases, you actually get optimal polynomial time algorithms, or you have some approximation. Okay. For this, there is like log Q approximation is known. So you have some algorithm, some oracle for solving the problem at hand. And now the next question is, what happens if you don't know the probability or you don't know the distribution? Can I use the same oracle in some black box manner, in some manner, to convert the offline solution to an online solution? That's the question. Does that make sense?
what is the online here?
Let me get to the online. Okay. So I'll just.
Static problem, Arpit, is it easier to sort of state if I can like probably so I mean let's say I like maybe cleaner formulation of maybe this is equivalent, but the sensor placement would be that give me a policy that covers with probability at least 1 minus delta and subject to that it's the subject to that the cost expected cost of
Yeah.
So then you can just write like minimize over S, like S being your adaptive policy, the expected cost of this subject to the fact that I mean, or even the
I will go through this is just for motivation. I go through the formal definition of the problem. So we'll define it. Okay, so yeah, I think it's similar to what you're saying. So the general problem can be defined in this way.
Opportunity is also kind of related where you also know the distribution. Does your framework also capture profits? Or?
Yeah, it does. Yeah, it does. So one thing to note about this is this term semi-bandit, right? So what's the reason for this term semi-bandit? So bandit feedback, there's two different feedbacks. One is bandit feedback and one is full feedback. And basically bandit feedback means like you get one feedback. Full feedback means you get full feedback on all items. Type of things that we're considering here is you inspect some S number of things. So you get like only on the inspected items you get feedback. That's why semi-bandit. Okay. So let me describe the setting formally. So you have a problem P, and in this problem you have n items. These are all stochastic items, and xi is drawn from a distribution di. So that this is the random variable for item I. Okay. It can be whether it survives or not, whether what's the reward, whatever, depending on the problem. Okay, and basically x1, x2. So x1, x2 of we have to xn are independent, but not IID, not necessarily IID. They are independent. And the goal is basically, so the problem is you want to maximize f of sigma, which is defined as the expected value. So this is the joint random variable drawn from the joint distribution of f sigma comma x, which is basically the, you can, if it is a cost function, it will be a minimization problem, but let's call it reward. So this is the reward for this realization of this random variable when policy sigma is executed, right? And then this is subject to some constraints. So sigma should belong to some set of C, which are basically a set of feasible policies.
Just to be slightly more forward, what is sigma? It's a function.
Yeah, now let's talk about what sigma is. Yeah. Okay, so sigma is basically a policy, and for simplicity, let's now assume that these are discrete distributions, like finite support distribution. Okay, so continuous is also possible, but let's say discrete, finite support, whatever. So sigma is a policy that's basically some adaptive policy, and each node of this policy is internally labeled with something, some criteria. So maybe like x1 is greater than some tau1, and then this is maybe x2 is greater than tau2. This can be x3 is greater than tau3, whatever. So it's basically an adaptive policy. Sometimes it could be like just a single tree, sorry, single chain. So it could also be like this. It could also be like an. Okay. So, for example, the first two that we saw, it was like this with a stopping rule. When do you want to stop? It could also be a general thing where you at every node you inspect some random variable, and based on what the value of that random variable is, you focus. So,
And when you say constraint, it's just that some property satisfied as the leaf.
some property satisfies the leaf. Yes, exactly. So this is the leaf node, and basically all the leaf nodes of this are basically feasible. That's basically the feasibility constraint. So yeah, it's a policy or a decision tree, and satisfies this property. And the leaf nodes are the termination nodes, and like S of sigma comma x is basically the set of items that are inspected for one path, and x is basically the full set of items, which determines which path you will take. Okay, so essentially we'll probe this partial set of items, and we are we are basically interested in polynomial time policies. Although like we could also have non-polynomial time policies, but primarily interested in polynomial time policies. It could be like optimal as well. Like the problem could be sort of tractable where you can compute the optimal policy in polynomial time, or it could be like non-tractable where you only have an approximation. Okay, so we will denote like sigma star as the optimal policy, and opt as the optimal value. And alpha is the approximation factor. So for like solvable tractable problems, alpha will be 1. For minimization problems, alpha will be greater than 1. And for maximization problems, alpha will be less than 1. Okay. So now this is the sort of entire problem set. Huh? Now let's come to the what is the online part of it. So the online setting. So I already sort of motivated this at the start, but once again, like if you, I think this is a very interesting sort of direction. Like if you are, let's say, solving, like let's say if you're one thing, for example, when like there's a lift or elevator that's tuned to certain distribution, right? But maybe that distribution that is tuned for is not the right distribution for your building. And can you sort of iteratively learn the particular distribution for your there's several, although we did like I don't know if that this thing works for scheduling or whatever, but that could be an open problem. But for example, revenue management, airline ticketing and all that, those are some problems that fit in a framework. Okay, so you have a time horizon T. Okay, and all these distributions are unknown to you. Okay. So in the classical settings, these are known and you go calculate optimal, but these are unknown to you. And for t is equal to 1 to t, you want to sort of you execute sigma t and you observe s sigma t comma xt. And then you basically update policy. This is your online setup. So at time t, you execute this policy sigma t, you observe some partial realization, you learn based on these partial realizations, you update your policy for the next round, and you iteratively go on. And then the question is, will this sigma t actually approach sigma? And for simplicity, today I will just cover the alpha is equal to 1 case. That you have a tractable thing, but you can also always multiply things with alpha and still goes to both.
Like just to be clear, like for the purposes of this setup, I can just think of policies as something that look at the history of realized rewards for the set you have selected, and then just picks another element to add to this. So it's just a sequence of sets, like it's a
You can
Markov
also
sequence of sets.
yeah.
Where you add a new
thing to that. Yeah.
every time.
Yeah.
And the point is that this feasibility just means that there's a collection of realized rewards. If you're if you match there, you're done.
Yeah.
And the distinction from the vanilla stochastic version is that you do not know DIs beforehand, like the bandit thing you are kind of learning.
Exactly. Yeah.
Okay.
Yeah. So just to as you said, mathematically defining it, like it's a function that takes in a partial set of observed items and outputs basically what is the next item that you need to observe.
And it's a single draw thing. Like you can't go back to the same.
No, you can't. Yeah.
Okay.
Oh, that's a very good point. Actually, you in these settings, you cannot like this. It's like single sample. Okay. You cannot. Maybe tomorrow it will be different.
Yeah.
But when you're executing that one single policy, it cannot be that you sample like this sensor failed one, then you put.
And put it back again.
Ah,
and try
yeah. But that's a very good point, which has to be made clear here. For t is equal to 1 to t, for a single execution, the random you can only sample once. Let's just keep this assumption, you can only sample once. But after the time period changes, you can then resample again.
No, say that again. So let's say I choose some sigma.
You choose some sigma, yeah.
Sigma, and I can I execute that same policy from 1 to t?
No, you can. So the distinction is that the inner loop is actually one execution of this setting.
Correct, correct. So basically, at small t, at each time step, I'm going to get one path traversal in that step.
Yes, for the sigma you have picked.
For this sigma epic. Yes, I completely agree.
Bits the catch that you the sigma, like you do not know the DIs before that.
Correct, correct. So one trivial policy would be I'll always keep sampling x1, right? I'll learn the distribution. For first
Very
ten
good.
steps,
Yeah.
I'll just keep learning
Very
x1.
good. Yeah.
I'll learn t1 and then I'll just put policy as sampling
Yes,
x2.
yes,
I'll
Yeah,
learn it.
very good, very good. Yeah.
Easily I can reach sigma
Yeah,
star.
yeah.
So there should be some cost
Yes, yes.
we want to minimize here.
Yes, yes, yes. Yeah, exactly. So going back to now the previous lecture, I discussed two algorithms.
Yeah.
One is explore then commit, which is exactly the type of strategy that you're describing.
Hmm.
And the other one was UCV.
Yeah.
And we'll see that algorithm where you just learning one x1, one x2, and so on has a higher cost.
And learning x1 first, x2.
X2 then and so on.
I see.
Because the thing is that for policy, you don't know whether x1 is actually important, an important node or not.
Correct.
Maybe some other node is a more important node, and you need to learn that first. Maybe that x1 comes very, very late on in the policy and doesn't really make a difference, or maybe never even picked, I guess.
You actually want to learn some, I mean, for example, the series testing,
Yeah.
which 1 minus pi by ci is the statistic you want to learn.
Exactly,
It's
exactly.
like a bandit algorithm where that is your actual.
Yeah, but it's much more complicated than that because it's a policy
Right.
at the end. It's not like yeah,
You have much more power. Like this is limiting yourself, like picking one.
Yeah.
variable.
yeah, exactly. Yeah.
So there are some policies.
Yeah.
There could be some policies which have a longer path.
Yeah.
Basically, I'm getting sample for each of those
Yes.
random variables.
Paying cost a bit more, whatever.
You pay cost in what factor? What is your cost? So, okay, he hasn't defined cost.
Oh, I see. So did I actually cost I haven't defined. Right. So
Just so, but every time you execute a policy, sigma t has to be feasible.
sigma t has to be feasible. That's the cost basically. So if it is a minimization problem,
Yeah.
right? So then f, this thing is your cost.
Correct.
F sigma x, you should think of it as a cost.
Yeah.
And then this sigma, this constraint, you should think of it as like in the submodular case, like that coverage value should be greater than q, whatever.
Yeah.
Okay, so if it's a reward problem, then like Pandoras.
So here every policy is just a permutation, right? And with these thresholdings.
Every policy can be thought of as a permute. It's not particularly a permutation. It could be adaptive also.
Okay, this is just tree.
It's a tree, yeah. It's a decision tree, yeah.
Decision tree.
Yeah.
Observe.
Because if this thing succeeds, maybe I don't need to sample x2 now. Maybe I could move on to other things. It's a tree. Also, like it normally gets a part. Okay, so moving on. We have very less time. So okay.
It's not like an improper learning framework where you can execute infeasible policies in the hopes of eventually like finding.
Yeah.
What is an infeasible policy here?
So for the submodular case, for example, right? You pick a subset and you see like it has some like you actually see if you pick this subset, these many sensors fail, and it might not cover everything. Like for example, the one you were saying, pick one sensor. That's not actually a feasible thing because a single sensor might not cover.
Right.
Yeah. Infeasible things are, let's say, not allowed, but even if you allow them,
Yeah, I see. Like you can just probably pad it with
Yeah.
constraint.
yeah, exactly. you just pay very high cost or something. But in the end, for bandit thing, it would not be very optimal. Okay, so basically, like I have this, and then I have defined what's the regret, what the regret is. So the regret is basically summation over t is equal to 1 to t, expected value of f. So this one is taken from x1, x2 to xt, and I always find it hard to hard to make a distinction between capital X and small x. In this lecture, I won't try to, but think of it as like a random, like a real expectation with respect to this particular random variable, and f sigma star x t minus f sigma t.
So you can treat each policy as an arm and also get a bound.
Yeah, that would be a very bad one. Yeah. Yeah, it could be infinity many, or
You
yeah,
can apply some epsilon approximation to
those sort of things. Yeah, you can do. But what you'll see is like much more elegant than that actually. So
Hard to sort of capture that.
yeah,
Case of policies.
yeah, it will also be very problem dependent actually. I think because it depends whether adaptive, whether what are the epsilon net. So yeah, so this is this clear, the definition of regret, right?
The notion of regret is like actually coming from what Kiran said. You are just seeing these as arms and the best arm is
Yeah,
sigma
yeah,
star
that is,
and
that is, yeah. But you're right. You can, but you can't do that in a sort of naive manner.
Yeah.
Right? You can't have anyone who's naive.
This can be capital B known or unknown? What?
Yeah, assume that it's known. You could do doubling and all that, but it's known. Okay, so this is also like. So this realizes this is opt. So this is expectation with respect to the particular xt of sigma star. Xt could like this thing doesn't depend on the fast history. And then this thing is, I'll write it as ht minus 1, and then expectation xt of f sigma t comma xt. Okay.
But just to piggyback on Kiran's question, things like follow the perturbed leader and all is difficult.
Follow the perturbed leader. Yeah. So typically, follow the perturbed leader is for adversarial problems.
Right.
So there are now works like this very recent development that you can use follow the perturbed leader for stochastic problems only. But it's typically for adversarial problems. And for this type of a setting, actually there are some offline to online conversions with follow the perturbed leader style of algorithms as well. But they are for adversarial settings. So Rad has had a paper on offline to online, where they use follow the perturbed leader. Their setting was more adversarial, so these rewards can be adversarially chosen, and but also their thing was very specific to the particular problem. So you have to actually be very specific. It's not like this general wide net which we can achieve for this. That would be another interesting problem. If you can actually achieve an adversarial type of problems, right? When the reward is chosen adversary, can you have this general type of reduction? Okay. So now the problem is clear. Now, can you sort of tell me some idea, like given that we saw the usage? Yeah, this is I sort of casually defined this notation, but this is the past x1 to xt minus 1, and this is xt. So
best policy as quickly as possible.
Yeah.
Are there some variants like that which makes sense in this case?
Best policy.
Sampling.
Best time identification.
Similar variant.
Those can also be asked. Yeah. I think I don't know the answer to those questions actually. Yeah, you can do explore then commit type things like, and yeah, but I don't know what's the optimal actually.
Yeah,
So, like,
Median selection that
Yeah.
those kind of elimination theory.
uh,
Similar some variant will be applicable here.
yeah. Yeah, so I think this is there are several questions here. I think this like even to more general problem setting, how do you do this offline to online? I think is the first one, but I think there's several other questions. Okay, so
In the Pandoras box setting, the like this would instantiate to you like picking boxes in a certain order and stopping at some point.
Yeah.
You'll get that set of rewards that's your first history. Based on that, you pick sigma 2, which is again a new order in a stopping route. Keep doing that.
you're doing that.
And
Yeah.
at the end, you're comparing with like a policy which would have known all the distributions.
Exactly.
The bit like the index policy.
Yeah.
Okay, is sigma star.
Yes. Yeah, exactly. So again, let me even so the regular definition is clear. Okay. So now let's say like what is given to me. So to me there is some alg that is given. Okay. And if I supply alg a distribution E, okay, it gives me a policy that's optimal for E. Okay, or approximately optimal if you are in the approximate setting. Okay, so alg basically returns. So I can use this as an oracle. Returns optimal.
Is a product distribution over.
In the product distribution, it's E1, E2, En. If you supply it the actual distribution D, it will give you the optimal policy sigma star. Optimal policy for E. So I'm given access to this oracle. Now I don't want to deal with like writing a new sort of fine-tuned whatever algorithm for each particular problem. The only information that I have about this problem is that I've been given. How do you then go about like developing an online solution? Like any thoughts based on what you have seen?
We effectively have to solve the UCB problem, like find a
Kind of UCB, yeah.
which has the highest.
Principle of optimism in the face of uncertainty.
You just play this, like you look at the distributions that you have observed and play, just supply that and play this, all this oracle play.
All this, yeah. That's a very good algorithm. There's a small thing that's missing, which is optimism.
Yeah.
So you're saying that you're taking the empirical distribution and just playing the empirical distribution. That also performs okay in practice actually, but it's very hard to. It's not known whether there is a bound or whether it performs well. And I think there can be counterexamples. I like, for example, even classical bandit. If you just keep playing the empirical distribution, there are counterexamples that you can't do. Can't get bounded in it. So you have to somehow embed the principle of optimism. And all will become clear like why you need to do that.
Confidence interval for empirical distribution.
Yeah.
Let's say these are all coins.
Yeah. So you want to do UCB.
So you shift the distributions up.
Yes, exactly. You shift the distribution first. That's basically the idea. Yeah. So Okay. So let me define the notion of sort of
In some sense, like the in UCB, R.v.s
Hmm.
is the like it will just keep return a single arm which has the highest mean. And so you shift the distributions of now you're saying you just have a general.
Yes, exactly. So in UCB, what you do is for Bernoulli distributions, what you do is you instead of playing mu hat, you increase mu hat by some epsilon amount, right? So basically you are increasing the probability of 1,
Yeah.
right? And reducing the probability of 0.
Sorry, I missed UCB. So UCB, how do you pick at each iteration?
Yeah, think of UCD that
Yeah.
instead of supplying mu hat, the empirical mean,
Yeah.
you supply like a pseudo mean,
Okay.
the empirical mu hat I plus the confidence.
Plus the confidence.
Yeah, so mu tilde I for it.
Mu tilde I.
And so the alg in that case just looks at the max mu tilde I and returns that. Now again, the Arpit's pointing
Once that, and here you look at the empirical distribution,
Yeah,
you shift it up, and then
Yeah.
play the maximum
optimal policy.
optimal policy for
For
that.
that,
No, you are shifting all of the. Basically, what you have from the past, you have learned distribution, approximate.
You have learned some CDF, yeah.
You have learned some joint product distribution.
Yes.
Approximate joint product distribution. You will shift this distribution.
For each item, each component you will shift upwards.
You will shift upwards.
Yeah.
And then invoke this.
Then invoke this, yes.
But in UCB, you are just invoking one arm, no? Here.
So UCB is sort of the max, right?
Yeah.
UCB, the alg is just the max.
Yeah.
Here the alg is some complicated sort of function. Some policy that takes into account like all these.
Oh, I see. Got it.
So in UCB also you shift everything up and then you just take the argmax. Here it's not an argmax, it's just some complicated sort of.
If the DIs were Bernoulli,
Yeah.
you would have just added a
Added a epsilon.
yeah.
For these multinomial distributions, it's slightly more complicated. Many ways to shift it upwards, but there is one way. That we have in the paper, basically. Okay. So let me just first define this notion of stochastic dominance here.
Yeah, exactly. I was about to say you still like have like push the mass.
Yes, push it up.
Yeah.
Okay, so this so okay, so E all right. So this is some notation for stochastic dominance. This E dominates the if the probability that this is the definition of stochastic dominance, and then what I will just tell you is that just a lemma. Believe me on this. So there exists an algorithm that basically takes as input some empirical distribution E. Okay, and let me actually refer to my notes for the exact. Okay, sorry. We are given m IID samples from D, and to assume that the support size is K. So support size for this distribution is K, and with probability, so delta is a parameter. Which is also given as input. And basically it computes some empirical distribution E such that one E stochastically dominates D. And then the second thing is that the total variation distance between E and D is less than equal to K square root log 2K over delta pi by 2. So just it's a simple sort of thing. You can just show like for a discrete distribution, just need to shift some mass up. And you want to do this in a way that first this is stochastic dominated, but you can't just shift all the mass to one, right? You have to do it in a sort of reasonable manner such that the total variation distance between empirical distribution and this E distribution and D distribution is bounded by this. It's just some sort of concentration inequality. So of course the true empirical distribution will satisfy this quantity, but it will not satisfy this quantity. So you want to shift some mass up from the empirical distribution so it satisfies this as well. Okay. So now given this, what I would show is that
Optimal transport or something.
you can use optimal transport sort of thing, but it's not that. Maybe for continuous distributions, you might want to use that. For discrete distribution, it is just very simple. Yeah. Yeah.
So if PV distance between two distributions is that much.
Yeah.
Then the difference can't I just add and make it stochastically dominant? I mean, I don't know how to add. If I promise you there are two distributions, D1 and D2, the TV distance is at most epsilon. Then can I?
You can make one to actually dominate. Yes.
Other by doing.
It's greedy, like the shifting from the left to the right.
Yeah, right. So the empirical itself, I need to shift.
The empirical, yeah.
A little bit. That factor will be 2 times.
2 times. Yes. Yeah. This is nothing complicated here. Just shift the empirical distribution upwards. So now we are ready
How
to.
is delta featuring here?
Here. This one.
That's fine, but take. M has to be some function. I see that, but
So this delta we will make it like 1 over T or something.
so finds it with probability at least 1 over delta. Like
Oh, sorry. Yeah. No, yeah.
computes it with probability.
With probability 1 over delta, it computes. Otherwise, no. Okay. So the. Okay, so now we are ready to sort of do this. Let me know when time is up. 5 minutes, okay. So
Take your time.
Yeah.
But we have this rule, right?
Yeah.
No, I want to see the thing.
okay. But we might actually it's slightly long. We might have to do one more session.
But yeah, like
But we can go as much as we can.
I'm standing.
Another day will be better.
Yeah.
I want meeting at 3.
Oh, 3.
You have 15 minutes.
Okay. Let's get through how much ever we can. Okay. So we.
It's already greedy for this year. Even for me, so it's true.
So for each item, calculate empirically, stochastically dominating distribution using that lemma, and call it epsilon I t. Okay, and then you sigma t is basically that alg of E1t t and then basically execute. Simple algorithm. We already sort of know this.
M that you're feeding is M for MIT.
MIT, yeah, the NIT or whatever. Yeah. So yeah, exactly. So when you call this algorithm, you give it all the past data that you have for this item. So all the times you have basically seen this item. And let's assume for now that you have seen the item, each item at least. So then you pass it to that algorithm and they'll compute this thing based on the past number of samples for each item in IT, and then you get the oracle. You call the oracle, gives you sigma t. Very simple algorithm. You don't need to know much about sort of this what this alg is and so on. Of course, you need to assume something about the problem itself, right? And it cannot be true for all possible sigmas and so on. So what is it that you need to assume about sigma, right? So that it works. Okay. And we want it to be like as broad as possible, like a very intuitive broad condition. And
warm starts would really help you here, like if you knew like distributions that are close to
Yeah.
PIs and
Yeah.
total variation, you could just start there and like
warm starts would be very helpful. Yes, yes, yes. So in fact, actually, like if you want to do this practically, and I mean this all said and done, this is actually practical. Because you can use it for many different like airline pricing and so on. And then if you have some data, then you will start it with the norms. Now it becomes slightly difficult to give you guarantees.
Yeah.
Like for bandits, it's like that cold start problem.
Yeah.
It's the results are not very meaningful then, because maybe you can have certain other distribution and so on. So if the results type of theoretical results you get is either too easy or too difficult, but in practice, having cold start, having a backlog of some empirical observations.
So it also touches upon this prior feature of like Thompson's sampling. You can think of these as when they're not data prior, but they are like prior, empirical priors to the and you're sort of the nice idea is doing this optimism thing.
Yeah, exactly. Yeah, if someone I think wants a low hanging fruit, that could be one. Like Thompson sampling version of this type of a thing. Oh, I shouldn't say low hanging. I actually didn't think about it. Maybe it's just I don't know. Okay. So this is very intuitive, very nice sort of algorithm. Doesn't require anything. Now, how do we actually understand what it does and for what sort of class of problems does it work? And that takes us. It's quite a quite an interesting sort of result. Okay, so
Guarantee and TV FLNT as bound where you can use it bound and you can define that.
Kind of lipstick test in the total variation distance.
Yeah.
Monotone speaking in this. Yeah. Like lipsticks and monotone in this.
Like
Easy.
UCP or the sub-Gaussian kind of assumption because you want to use counting or something. Here you need some similar assumptions or
let's maybe get into the but I see you're not able to sort of make the connection. That's the point that you're trying.
no, I'm trying to understand like what is the like property you're looking for? I mean, you're trying to find for what kind of policies problems it will work. So how do you kind of quantify the property of the problem?
That's very. It took us some time to figure that out, but it's actually sort of the answer was kind of in hindsight it was staring at our face given the sort of type of this thing is.
There has to be some difference. Like it cannot be that I change the distribution ever so slightly in the optimal policy. like the cost of the optimal policy is drastically.
You don't need Lipschitzness actually. It's a very, the only thing that you need is monotonicity. You can have many sort of variations of monotonicity. So you can have up monotonicity, down monotonicity, whatever, but I'll describe up monotonicity. And for any sort of upward monotonicity minimization problem, maximization problem, this thing works, but I'll just choose maximization problem and up monotonicity. Okay. So basically this says is that if some epsilon, sorry, not epsilon, empirical, some distribution E stochastically dominates distribution D, then the opt under E has to be larger than the opt under D. That's it. So very, very natural, like many problems satisfy this type of model. Like Pandoras box, like increase the rewards for everything, the what you can get will increase. Right? Keep the cost same, increase the rewards. Monotonically for each one, you will actually get better out. Right? So very natural sort of condition, but it's also not satisfied for many other problems, but definitely satisfied for many problems. Okay. Yeah, so like matching might be an example where it's not satisfied. There's some other like I think for operations people is some score function classification and all these sort of problems and so on. But there could be many other examples, like many other problems in like auctions and all that might not satisfy monotonicity.
I mean, even Siddharth's fitness might also give you some parameter element that you can take the UCB proof and change it easily. It can be done.
Okay, you're talking about Lipschitzness, and if I have Lipschitzness, then would it give me something directly? Right.
Which is stronger, like Lipschitzness is.
It's slightly stronger than
I mean, it's much stronger than monotonicity.
Yeah,
I mean, it pretty much writes the proof in the sense that. So you have this TV distance, and the sigma, once these ETs are close enough to your true distributions, Lipschitz would tell you that the optimal policy with respect to ET is like lambda or whatever, Lipschitz times the thing. So it's just that comes out as a fact.
Monotonicity and Lipschitzness are incomparable.
So incomparable because you could have like discontinuities.
Correct.
I mean, monotone just says the function is, there can be a step function and increase. Lipschitz can go down
and up.
Yeah.
So it can, I mean, both are
complementary.
Yeah. I mean,
but I do think that for especially for combinatorial optimization, assuming Lipschitzness is like a bit too much.
It is.
Because you don't know whether like just some maybe like some tweaking parameter makes you fall over the edge and then the solution completely changes, right? And you get like.
so the interesting thing here is to define this property, which captures all the your existing problems that you wanted to solve.
Yeah.
And you said you goes through.
Yes. But
finding that property
is basically a very important step in this. Like if you like the proof also is not like super simple. Like okay, it's quite non-trivial actually. Because it's not doesn't direct like if you give me like you have to spend lots and lots of time even given this. But I think realizing this is also like an important step in this. I think the first for the proof. Okay.
Let's say the proof is post-certified. I mean,
yeah, but I think this sort of this monotonicity condition that like nicely makes it like, well, I've seen this type of algorithm before. So, like people have people say that, oh, we tried putting in Pelka distribution and tried to run this and so on, it works. But having this sort of this very large framework and capturing it through Monotone is actually very nice. Okay. So let me try to have like 10 minutes maybe. So
Yeah. I think we should meet again sometime.
Yeah.
okay. So should we
Yeah, you just tell us like so this sort of is the main thing. So what is the theorem statement? Maybe you
Yeah.
just say that and
It is your regret problem.
yeah.
yeah, so basically the theorem statement is the following. So um let me actually
So you don't need any further assumption on F, that reward function and the class of policies or anything. Right? Just
No.
property.
this thing, yeah. Yeah. So we go to the paper.
Mhm.
Right.
And also, I think interestingly, it's the off that you are okay.
Yeah, okay. So you have a problem P.
With that, pushing up, they were all in upper bounds for nice part. So,
So, but the catch is that you do get sigma t for this thing, but you are still applying sigma t on the two unknown distance. If that
right, even there, you pick the max.
What if you come to approximate monocyte doesn't like even it's not always nothing but alpha times of it is more than
then it's
of the, then do you still get some guarantee or it's not clear?
Alpha time. Oh, I think you should get. Yeah, I think you should get even for that. I think we didn't sort of write. Maybe we discussed it, but I think you should get because yeah, I think the proof should go through. But yeah. Because we have this result for approximate. So anyway, there's an alpha everywhere when we are invoking these things. So okay, so you have the following theorem. So problem P, and there exists alg, which gives alpha approximate solution sigma, and there exists sorry, yeah, and then also P satisfies so up or down monotone setting. Then there exists a poly time online semi-bandit. To Gautam, which has with alpha regret. this is the theorem. So alpha regret, I forgot to define, but alpha, like you just multiply the opt by alpha basically in the regret definition. But for alpha is equal to 1, it's clear. So you have an algorithm that gives you an alpha approximation, policy sigma. You can use that algorithm to have a online semi-bandit algorithm, and with alpha regret this. This n is the number of items, k is the support size of the distribution, f max is the maximum function value. So yeah, it does depend on the maximum value. And then square root t log kt. Yeah. So this is basically the statement of the theorem. Let me give you one bit of sort of. So that new proof of UCB actually is very important in this, and it will become sort of clear in when I describe the proof to you that you can actually use it. But it's not like, again, it's a very important thing. So in UCB, what you do is I'll basically lead with the challenge. So in UCB, you have an option to play a noun, right? Here you don't have an option to play a noun. Like you execute the policy does whatever it does. It plays arm1, arm2, or whatever, it plays some items, and you have no control on it, right? So in the UCB, it sort of manages the explore exploit trade-off explicitly. That if this arm is like less played, you know less about it, you can play it next iteration. But here you don't know, like maybe some arm is less played. In the next round you update your policy. You don't know whether that arm will be played. Maybe it's not important for the policy. So you cannot get a like complete bound on like how much I am learning about the particular arm actually. Because that all depends how important that arm is for that policy. So how do you then sort of measure this progress in terms of the number of times an item is played? You have no control over it. That makes it quite challenging. Does that?
Yeah. Maybe sigma t is coming from black box algorithm.
Yeah, exactly. Because in your UCB we use NIT everywhere, right? And we sort of show that the suboptimality depends on NIT. Here you have no handle on what NIT is. That's
If lower bound of this can get at least like T log KT or something from real life.
if you want a lower bound, I mean the multi-bandit is a special case of this.
Already there, but you also like if math etc. those also come into the lower bound already, or what do you know about the lower bound?
It can come from this, the coin there is 0, 1. I think you push it to 0 to B, then B appears. Don't let it.
One nice thing about the proof that he said was it was like the more Slipkin's kind of proof bounds NIT.
Yeah.
Here you actually managed to never touch that.
Never touch that, yeah. Yes. That was actually the very critical moment in this sort of journey where I realized that this sort of proof is there.
It never touches.
It never touches NIT. And whatever value it takes down the line, you don't care, like as long as
Slipkin's and like Latimer's proof, they show that for high delta I, NIT is low.
NIT is low, yeah.
You don't bound. Yeah, it's good to know like 7, 8 proofs of a single zero.
Yeah.
Very nice.
Yeah, so maybe we'll stop here, and then next time we can tell you like
When should we next day? So tomorrow is holiday.
Thursday.
That's actually I'm not very good.